Welcome. In this video lesson, we are going to take a look at one of, in my opinion, the coolest models in dealing with differential equations, and this is called the SIR model. It is a homogeneous, first-order, non-linear system of differential equations. And this is a model used to model things such as the current COVID-19 outbreak. The Center for Disease Control and Prevention specializes in monitoring outbreaks and diseases and influenzas worldwide. In 2009, for example, H1N1 flu, also known as the swine flu, caused an outbreak across the world at pandemic levels. Eventually, however, the flu lost momentum and nearly disappeared by spring of 2010. On this very day, as this video is being recorded, we are facing the COVID-19 pandemic, and this pandemic can be modeled using SIR as well. Though pandemics are difficult to control, they can be modeled quite usefully by the use of the SIR model developed by Kermack and McKendrick back in 1927. The model keeps track of rates of change associated with three types of individuals. Those susceptible to getting the condition, so this means that you do not currently have the infection, but that if you made contact with someone who did, that you could acquire that condition or that infection. Those who are actually infected, so those are the people who currently are sick. In terms of the context of COVID-19, if those of us who are staying home and minding our quarantines, susceptible, we're all susceptible. The people who are infected are the ones who are currently ill, and those who have recovered. A lot of times this is actually called the removed group because it includes anyone who is immune or anyone who may have passed away as a result of having that particular infection. Now, in order to develop this model, we're going to try to make some relationships among these three groups. We first need to make some assumptions, and these are base level assumptions. They aren't completely valid in the real world, but you have to start somewhere with a model. So SIR is a set of all individuals, and they fall into one of the following categories. So everybody, for example, in the United States can be classified as susceptible, those who can catch the disease, infectious, those who can spread the disease, or the people who currently have the infection, and the removed, those who are immune and cannot spread the disease. Again, removed just sort of models everybody who is not susceptible and infected, whether that means they've been vaccinated or have passed away or have recovered from the disease and cannot get it again. We also assume the population is large but fixed in size and confined to a well-defined region. You might imagine the population to be a large university during the semester when relatively little outside travel takes place. We also assume the population is well mixed. Ideally, everyone comes in contact with the same fraction of people in each category each day. Imagine the multitude of contacts a student makes daily at a large university. So we assume that these contacts are somewhat random in the sense that the person who you contact there's a probability that they're susceptible, that they're infected, that they're removed, based on the proportion of people who fall into each of these groups. So we have this compartmental model. It's sort of like the idea of the compartmental tank models where we have one tank flowing into another, but the flow actually occurs from susceptible to infected to removed, meaning that at some point everybody will become part of the removed group, and at time zero a certain percentage may start in each one of these three groups. Notice that we assume people cannot become reinfected. Our model does not allow for people who are removed to become susceptible or to become infected again. So that's a limitation of this model already. And with infections or pandemics like COVID-19, where there is a probability, and we've seen some reinfections for people who have had it, who have recovered, and somehow have received positive test results again, this may not be the exact model for it, but again, it's a baseline. In building the system of three differential equations, we define four variables. We have our independent variable, t, which is the time in days, with t equals 0 at the start of observation. Days just make sense for things that evolve rapidly, like flus and communicable diseases. For things like HIV, days may not make a big difference. It may be a matter of months or years. S, I, and R represent the number of susceptible, infectious, and removed individuals. we're going to begin building the rate at which people become infected. So we assumed that our population is large and well mixed. That is, even though this is not an exact science, we will assume that the number of people infected will be evenly distributed across the sickness period. Suppose that the flu is active in a person for an average of 5 days. At what rate, di out dt, will people become immune? Okay, so that's di dt is going to consist of two pieces. It's going to have di in, the rate at which people become infected, minus the rate at which people leave the infected state and become removed. So that this di in represents this arrow coming into the infected group. The di out represents the people leaving the infected group into the removed group. We're focusing on this piece here. Now here we're saying that people are evenly distributed across the 5 days. So if I visualize how to work with this 5 days, here's time 0, 1, 2, 3, 4, and 5. And this is t 0, 1, 2, 3, 4, 5. If I have, let's say I have 10 people in my population, then by assumption, we're saying that basically there are 2 people within each of these 5 days, or these 5 periods. So there are 2 people. If I have a population of n equals 10 people that are infected, or maybe I'm not going to use n, I have 10 people who are infected, then those 10 people, we're assuming that because the population is large and well mixed, by that virtue, it makes sense to assume that an equal proportion of 1/5 of the population is in each of these stages. So let's say 1 day passes. Well, if 1 day passes, these 2 people here who are on their way out, they will leave the infected state. If we imagine this whole thing to represent the number of infected at time t, then 2 of them will leave. Well, 2 out of 10 people is 1/5. So the rate at which people leave is 1/5 of the total number of people in there. So if we took 1/5 of the 10 people who are infected, that means 2 of them would leave the infected group and would become removed. These people are traveling to the removed group. So to get di out dt, all we need to take into account is the fact that di out dt is 1/5 of the current number of infected. So that's going to be 1/5 of the number of infected will be leaving the infected group by virtue of our assumption that the population is well mixed. Now, if everybody suddenly got sick, clearly this wouldn't make sense for a few days until the infection kind of caused people to distribute across those 5 days of the sickness period, but this is a good enough assumption for now. So there's our final answer for what di out dt will look like. Great. So we know in our picture up here, we know that this is going to be 1/5 of I. Now we generalize di out dt. Suppose a person is sick for b days. What is di out dt in terms of this parameter? Well, really, if this were a 10-day period and people were equally distributed across the 10 days, we would have taken 1/10 of I. And so in general, we could say that di out dt is equal to 1 over b times I, where b is the number of days of the sickness. Great. Okay, so we are now ready to model the rate at which susceptibles become infected. So remember that the people who are coming into the infected group are the people who are currently susceptible, and we need to know how a susceptible person would become infected. In order to do this, we assume that each infected person makes an average total number of close contacts with other people across their illness. So basically, we're going to assume that each person makes, let's say, 15 contacts on average. It's going to be average. Everybody's a little bit different. Some will make no contact. Some will make a lot of contact. But you got to make an assumption. You cannot analyze individuals at the individual level. We'll also assume the disease has some level of contagiousness, such that some known percentage of close contacts with infected result in the disease spreading to the person susceptible. So imagine a person is sick with the flu for an average of 5 days. He or she makes a total of 40 contacts across their sickness. There is a 25% chance that contact with a susceptible person, that person catches the flu from an ill person. For the current time, assume there are 50 susceptible, 30 ill, and we have a population of 100 people, so that means that 20 are in the removed group. So if we model S at the current time is 50, and the number of infected is 30, and the number of removed is therefore 20. So again, we have assumed everybody has their place. With that being the case, S equals 50, I equals 30, R equals 20. First of all, it makes sense to say, okay, they're sick across a 5-day period. We know that DI dt, its units, have to be the number of infected per day. And so, first of all, this is 40 contacts across their sickness. Well, that's only for all of the days. So each infected, we have 40 contacts per one infected per 1 day. Right? So each infected person is going to make 40 contacts every day on average. Now we need to that's across 1 day, so we need to divide that by 5 days, because that's, oh, I'm sorry, this is not per day, this is per infected. So we'll just say per infected. Okay, so 1 infected, and we need to divide that by 5 days, which will leave us with 8 contacts per 1 infected per 1 day. And that's, again, just an average, but it's good enough. And now that we know that, not all those 8 contacts that each person is going to make is going to be with a susceptible person, right? Because only contacts that an infected person makes with a susceptible person can result in an infection. So of those, we have to think about, if they make 8 contacts and we break up the population, we know that right now 50% of those contacts are going to be with a susceptible person. So of the 8 contacts per 1 infected per 1 day, we know that 50 people are susceptible, but we want to know the fraction or the percentage of those contacts that will be with a susceptible. So this right here is percentage of susceptible. And that's going to give us 4 contacts per 1 infected per 1 day. And this particular contact this is 4 contacts with a susceptible. So I'm going to modify the units a little bit. So with a susceptible person. So every infected person is going to contact 4 susceptible people. Now, just because they make contact, that an infected person has what we consider close contact with a susceptible person, that doesn't mean they're going to catch the sickness. There's only a 25% chance that contact with a susceptible person will result in the flu being transferred. So 25% is the same thing as saying 25% of all contacts of a susceptible with an infected person will result in infection. So now we're going to take this 4 contacts with a susceptible per 1 infected per day. Let's try that one more time here. One more time. Okay, there we go. All right. And so there we have our rate, and now we know that only 25% of those contacts are going to result in an infection. So we'll multiply this by the 25% chance, and so we're only going to get one contact with susceptible per one infected per 1 day, and this is the number of new infections. So you can think about this as infections per day. So maybe I don't even want to call this contact anymore. Maybe I just want to call this infections. So one infection per one infected person. So one infected person will cause one infection per 1 day. Awesome, almost there. So now that we know how many infections each infected person will cause, now there are 30 infected people, so we need to take that rate. We need to take one infection per one infected person per 1 day, multiplied by the number of infected people, which is 30 infected, and those infected units will cancel, and now I have 30 infections per 1 day, which matches my units up here. And now we know how many new infections there should be tomorrow. There should be 30 new people infected. And that's a lot, right? Because each of these 30 people caused one infection, and so 30 of these 50 people are now going to move over to the infected group. 1/5 of these 30 people are going to become removed, and now there are only 20 susceptible. But that's assuming a discrete model. We have a continuous model. Now let's try to generalize this. A person with the flu is sick for an average of B days. He or she will make a total of C contacts across their sickness. We know there is a P times 100% chance that contact with a susceptible person catches the flu from an ill person. So P times 100% just means that, or P times 100 will give us the percentage version of it. So we assume P is in decimal form so that we don't have to divide it by 100. Suppose there are S people susceptible, I are ill, and the population size is N people large. How many new infections should we expect tomorrow? That is, what is DIN dt? So that's what we computed above. In problem 3, we computed this, but we computed it with numbers. So what did we have to start with? Well, we started with the number of contacts across the sick period divided by the number of days. So we know that a person makes C contacts across B days. And so that's going to give us what we have up here. That would have given us our 8. Now we had to multiply that by the number of susceptible divided by the population size. So we had to multiply that by capital S times little n. And that gave us the number of contacts with the susceptible that an infected would make each day. Then we had to multiply that result by P, which is the probability that the infection spreads. And once we had that one infection with a susceptible per one infected per 1 day, then we had to multiply it by the number of infected, which is characterized by the variable I. And there we go. So this looks like a big, messy thing. We have, notice, 2 dependent variables here. We have S and we have I. The rest are all just constants. S and I are allowed to change. So di dt is going to be the difference between the people coming in and the people coming out, or the rate at which they come in and come out. Di out dt. Di in we just established as this, so C over B, I'm going to write this times P times S over N times I. And then minus di out dt, well, we assumed that that was like 1/5 of the population, but in general it was 1 over however many days the person has it for. times the number of infected. And so there is our di dt. Now that looks really messy, but keep in mind that that is the hardest piece of this puzzle. Now what is our final ds dt equation? Well, let's think about this. Our compartments basically say that what comes out of the susceptible group is exactly what goes into the infected group. So ds dt does not have a ds in because people are not becoming susceptible. They either start susceptible, but they cannot become susceptible later because the trickle goes from susceptible to removed. So this right here is precisely di in dt. And so what comes out of susceptible, di in is, what comes out of susceptible is what goes in to the infected group. So ds dt is going to equal what comes in to di dt, which is c over b times p times s over n times I. So that's exactly what goes in to what comes out of ds dt. So I'll also have to have a negative sign here, right? Because this is the outflow. It's coming out of the susceptible group, but that is precisely what's going in to the infected group. Now what's going into the removed group is what's coming out of the infected group, right? That's going to be what comes out of the infected group, because everybody who leaves the infected group is becoming part of the removed group, and that is simply this term here, but it's positive because these people are coming into the removed group. So 1 over b times I, those are the people leaving the infected group, arriving at the removed group. Okay, these models work well, but oftentimes we don't want to model the number of sick people. We would rather express it in terms of percentages. So right now with the COVID-19 pandemic, you see reports of the number of people who have the condition. But a lot of times, in order to be able to compare regions that have different population sizes, New York, for example, is very densely populated where a lot of those infections are coming around. The Phoenix area, where I'm reporting from during this video, is in the suburbs, a little less densely populated, and people do not cross paths as often. So it makes sense to talk about proportions instead. So these models work well, but most disease studies center around the proportion of people who are in each group so that disease can be compared across different geographic regions with different population sizes. Denote little s to be capital S divided by n. So take the number of susceptible people, divide it by the population size. That gives you the proportion of the population that is susceptible. And similarly, little I will equal capital I divided by n, not to be confused with the complex number. That's not what we're talking about here. And little r will be the proportion of people who are removed. So if we take our original ds dt model, this guy here, which was the big messy thing, CB, I'll write it like this, C times P divided by B times S over N times I, and that's a negative because those are people leaving the susceptible group, nobody's arriving there. And if what I did is I multiplied both sides by 1 over n times 1 over n, then because the derivative of s, because this is a constant, one thing that I can do here is I can write this as ddt of the derivative of s divided by little n. So if you scale a function down, it doesn't affect its derivative function, it just gets scaled by little n. And because of that, this is really the derivative of little s, and check out what happens here. I divided by I divided by n is little I, s divided by little n, conveniently, is little s, and so now we have negative CP over B. So if for all of these equations we divide by n, here we had also the same term, so little s times little I, that's going to be the same as there and there. And then here we just have that 1 over little b times I. And if we divide both sides of, if we divide right here, if we divide I by little n, we get little I as well. So anyway, we could do that, get all of these to be proportions. And notice that now we're saying negative alpha si. So this whole thing here, this guy is what we're going to be calling the negative of alpha. All these parameters, alpha and beta, are actually non-negative constants. So if we want to make them negative, we've got to put the negative sign in front of them. So it just makes the model look a little prettier. You could see that what comes out of susceptible is what comes into infected. What comes out of infected is what comes into the removed group. And now down here we'll just say alpha is actually C times P over B. Beta, that's this guy here, is really just the 1 over little b, the 1 divided by the number of days the person is infected for. B is the number of days of infection, C is the total number of contacts made by infected, and P is the proportion of contacts with susceptible that spread the illness. A lot of times you'll hear, and in movies like the movie Contagion, alpha is often called the contagion parameter because it describes at what rate people become infected. And beta is the recovery rate parameter because it describes how rapidly people become recovered. So when you see this model at first, you see these interaction terms. And with the predator-prey models, it's a similar type of development for those models as well, that S times I is actually an interaction, but it became very intuitive to develop that S times I in there because of the legwork we did up here. So you can see that that interaction term is going to be affected by how many susceptible and infected there are, because that's how disease spreads, as susceptible people interact with people who have a sickness. Pretty cool stuff. And so we often, as a side note, disregard dr dt, since neither of the first two groups depend on this function, nor its dependent variable. Also, anyone who is not susceptible or infected is automatically removed, is recovered. So you can see that here dr dt depends on I, but neither ds dt nor di dt depend on R. So because people are not allowed to become susceptible or infected in this model assumption, we really can ignore this. And if we add up the proportion who are susceptible and infected and they add up to 78%, well then 22% of people are removed. So when we're going to analyze this, we're just going to focus on these two models. So in the analysis that follows, we'll assume that B equals 5 days of flu, C equals 40 total contacts made by infected, and P equals 0.25, so that ds dt equals negative 2si. So the negative 2 comes from 40 divided by 5 is 8 times 0.25 is 2, and this is going to be negative alpha. And this 0.2 is just 1/5. So 1/5 of 5 days, or 1/5 is, yeah, there we go. Okay, good. So there's our model, and let's do an analysis. So this is a nonlinear system, so we would need to consider equilibrium points and try to understand what's happening. It makes sense to do a nullcline analysis. And so here we have the output from Wolfram Alpha. Notice that since we're using these symbols S and I had to put multiplication signs between them. If you're using X and Y, it's not as much of an issue. But notice that it says assuming I is a variable. It was originally interpreted as the imaginary unit, the square root of -1. So there's a little button off to the side here that if initially it says assuming I is the imaginary unit, you got to change it to a variable. And so when I find the solution, that is setting both of these rates equal to 0, I get I equals 0. And that's kind of funny, because that's not a point. I equals 0 is a whole set of points. So for example, as long as I is 0, as long as I equals 0, we are in equilibrium. Well, what does that mean exactly? Well, that means that the only way, the one and only way for this system to produce equilibrium values is for I to be 0. And I shouldn't say that's one way, but it requires that I be equal to 0. It's not sufficient for S to be equal to 0, because if you notice if S is 0, if 0% of people are susceptible, then if there are still people who are infected, then they may be moving to the removed group. If S is 0, though, it just simply means that nobody can move from susceptible to the infected group, that basically there's nobody to get sickness anymore. But just because there are 0 susceptible doesn't mean that there aren't any infected, and as long as they're infected, then people are becoming removed on a daily basis. So the only way for this sickness to end is really for there to be 0 people infected. And so any point of the form S comma 0, where little s and little I are equal to this ordered pair. So, for example, there could be 100% of people could be susceptible, but as long as there's nobody who's infected, then there's nobody to spread the sickness. So the only way that there could be activity is if there are infected people. If there aren't any infected people, you don't have an epidemic, you don't have a sickness, you certainly don't have a pandemic where something is spreading globally. And that's, by the way, all a pandemic means, is that it's spreading beyond, I think, so many countries that they emphasize. Now, for example, 20% of people could be susceptible, but as long as there's nobody infected, then we're all good. There's no spread of infection. There's not going to be any movement from susceptible to infected or infected to removed. So this is a weird kind of equilibrium point where it's actually a whole line of equilibrium values. And we're going to analyze that next and see what happens when we look at the nullclines. So to classify this equilibrium point is going to be a little bit tricky, because our Jacobian matrix is going to be the partial with respect to all of these variables. So ds dt, its partial would be, with respect to s, it would be negative 2i. And with respect to I, it would be negative 2s. And the partial of this guy, di dt, with respect to s will be 2i. And the derivative of this guy with respect to I will be, let's see, 2s minus 0.2. So the tricky part is, because this is not just one equilibrium point, it's a whole multitude of them, then the only thing I can really do is just, if I want to encompass all of these different equilibrium points, is to plug in 0 for I and plug in s for s. I mean, really, there are infinitely many possible values. If I plug in 0 for I, I'll have 0, negative 2s, 0, and 2s minus 0.2. And so I can still, I see that the determinant is 0, because 0 times this will be 0 minus 0 times this guy will be 0. So the linearization theorem doesn't tell us anything. Bummer. So this is one of the disadvantages of that, is that if you get these weird kind of equilibrium points, a lot of times you may not have solutions. So now what I want to do is plot the nullclines. So what I'm going to decide to do is I will keep track of the number of susceptible on the horizontal axis, infected on the vertical axis, and we're only going to focus on the first quadrant. So let's go ahead and find the S nullclines. They're not really X nullclines, they're S nullclines. And let's do that next. So in our S nullclines, we have two nullclines. One is I equals 0, and the other is S equals 0. This is not the point 0, 0. This is just the values of I and S that cause ds dt to be 0. So I equals 0 is the same thing as saying y equals 0, and that is all the way across the S axis, like so. And we can go ahead and make this just a little bolder. All right, there we go. And now we'll do the same thing for S equals 0, which is a vertical line. And you can see we have these nullclines just broke up the plane into 4 quadrants, the first, second, third, and fourth. We're only focusing on this one. So we're just going to pick one test point in that region, one pair Si and calculate the sign of ds dt in that quadrant. So, for example, we could pick one. By the way, 1, 1 is not a valid point. The only points that we could have, in fact, can fall only along this diagonal, because we have to make sure that s plus I equals 1, which means that I equals 1 minus s, or y equals 1 minus x. So only conditions on or below this line are feasible. So if we pick 0.5, 0.5, for instance, right, because if we had let's say 1, 1, we would be saying 100% of people are susceptible and 100% of people are infected, but that can't be. So if we plug in 0.5 and 0.5 for s and I, we'll get negative 2 times a half, which is negative a half, and that's going to be a negative value. Now s is right and left, so having a negative ds dt means all the vectors inside of this region will point left. So what does that mean? Well, that means that instantly, at any initial condition you pick, the number of susceptibles is going to be decaying down to 0, which makes total sense because susceptibles are becoming infected. Now, if you have the I nullclines, we have 2 of them. We have I equals 0 and s is about 0.1. So for I equals 0 is, again, this line here. And s equals 0.1 is right about here. So right there, that's an interesting place for a nullcline. And the thing that we should now check is we have really 2 regions. Well, we have 4 regions. This region to the top left, top right, bottom left, bottom right. But we're only interested in these 2 regions here because that's part of our first quadrant. So I'm going to pick a ordered pair in each of those 2 regions to check the sign of di dt. These are going to be up or down vectors. So for instance, in this interval, I could pick like 0, 1. Let's go with 0, 1. That seems reasonable. 0, 1. So if I plug in 0 for s, this first term is 0, minus 0.2 times 1 is negative. So this is going to be a downward vector. And then at, let's say, 0.5, 0.5. It's okay to pick something like 1, 1. It's just know that it's not a feasible value for our model, but it does fall within that top right quadrant. And so if we plug this in, we'll have 2 times 0.5 times 0.5, which is a half. 0.2 times 0.5 times 0.5 is definitely less than a half, so this will end up being positive, which means the arrows point upwards. So it seems like once the number of susceptible get beyond 10%, the number of infecteds begin to drop. But as long as the susceptibles are 0.1 to 1 somewhere, then the the infected population is going to be on the rise. So let's put these 2 analyses together. So here I have my X nullclines, and now I'm going to superimpose these other guys over it. So one of the interesting things to note is that the S-axis has 2 nullclines on it, right? So both nullclines, this is both an S and I nullcline. Well, that should make sense because anytime 2 nullclines meet, that's an equilibrium point. And so that just justifies the equilibrium point that we found. Every point on this line is an equilibrium point. So any point where s, I equals some value of s, but 0 for I, which is every point along here, along this thing here, every single point along there acts as an equilibrium point. We've seen this before where there are 0 eigenvalues that end up being 0. These points can act as attractors. Very nice. Okay, so now we have the second nullcline for I, so that's this one here. And now, so we know that over to the left of this line, the arrows are also pointing left because it's still part of that top right region. But now we know that based on our y nullclines, that the y component of the vectors to the left of s equals 0.1 point down, and here they point up. So one possible thing we should see is if we started, like, let's say at 0.5, 0.5, we would probably see something like this. Now we hit an I nullcline. An I nullcline does not point up or point down. You can see here the pink arrow points down, here it points up. They clash. That emphasizes that this is an I nullcline, but the green vectors are both pointing to the right, so this point will pass through here. And now that point is limited to downward travel. If it does hit this nullcline here, which it doesn't really make sense because, I guess it does, that could happen, but we'll probably see something like this. If it ever does hit this S nullcline, that just means that we're only going to have downward travel, and so this point will end up somewhere down here. So if you think about it, the equilibrium point for this particular set of values is going to fall somewhere between s equals 0 and s equals 0.1. So at the end of the day, there will be still some susceptible, but if the number of infected hits 0 before all of the susceptibles get the disease, then there are still going to be people who never ever got the disease. And that's kind of the idea with things like COVID-19. So that's pretty neat. We said earlier that all ordered pairs Si equals S0, 0 for any real number S0 are all equilibrium points that cannot be classified by the linearization theorem since the determinant of the Jacobian matrix is 0. What can we conclude with certainty about all long-run behaviors of this system within the constraint region? 0, S is between 0 and 1, and I is between 0 and 1. So we'll say something like this. S will approach S equals 0.1, while I rises. When S is less than 0.1, that's the portion where we hit this side of the S nullcline, of the I nullcline, excuse me, I decays, and S will, S final, we'll call this S final, the value of S will end up somewhere between 0 and 0.1. Very cool. So that gives us a good analysis of this system. Let's go ahead and take a look at the graph or phase plane as well. So here we can actually relabel our variables S and I, and this is -2 times S times I. And this one we'll call di dt, so this will be 2 times S times I minus 0.2 times I. And we want, let's see, we want this axis to be the I-axis, and we want this axis to be the S-axis. So there we go. And let's just go ahead and take a look at, and here we'll also do, we want this to be I versus time, and we want this to be S versus time. There we go. So depending on what initial condition we pick, let's clear all the initial conditions for now. And let's change our window. We don't need to go from 0 to 10. We really just need to be from 0% to 100% and from 0 to 100%. And again, for whatever reason, this doesn't like those square boundaries. So let's see. And here you can see all of these trajectories look just as we had predicted. And you can see that depending on what the initial condition is, that we get a little bit of a rise. Now, depending on where we start, if we start with fewer susceptible than 0.1, then immediately the number of infected over time begins to decay. There are still people becoming infected, but they're becoming removed faster than they are becoming infected. If you start off with an equilibrium point like down over here somewhere, what you're actually getting is called an epidemic. An epidemic is where the proportion of people who are infected is growing. Now, yeah, people become infected, but people are becoming removed as well. And when people are becoming infected faster than they are becoming removed, then that means you have what's called an epidemic. So right here we have an epidemic because the number of infected is on the rise. The infected proportion is getting bigger and bigger, but then the pandemic ends when this thing peaks, and this is called the top of that curve. The thing that they've been talking a lot about, when does the COVID-19 curve peak? Well, it peaks whenever the number of people becoming susceptible happens at a faster rate than the rate at which people are becoming infected. Now keep in mind this was very specific to our parameters. We could try different parameters like the probability of infection is bigger or smaller, what happens if people are not quarantining. If everybody were quarantining, then these parameters would be 0. And if this was 0 and this was 0 down here, right, then basically unless there were people that initially got the disease, then you could see that the number of infected just drops to 0. There's no change in the number of susceptible because nobody's becoming infected since everybody's quarantining. And you can see what would happen if you made that a little bit smaller than the previous parameter. And you can see that that curve happens a lot faster. It peaks a lot faster. And you can see here where now one of the nullclines has shifted from s equals 0.1 to about s equals 0.2. Pretty interesting stuff what you can do with these models. Now we said we can't solve these, but there is a pretty cool little trick that I want to show you about how you can actually solve a differential equation sometimes. The system above cannot be solved, however we can exploit it for an interesting solution. Observe what happens with the ratio below. So if we divide the I prime by the s prime, the two rates, then the dt's cancel, and we're left with di over ds, a brand new differential equation. If we do a little bit of simplification here and write this as 2si over 2si minus 0.2i over 2si, these cancel. We're left with 1 minus 0.2 divided by 2 is 0.1, I believe. And so then the two i's cancel here, and we're just left with 1 over s, which can obviously be written as di ds equals 1 minus 0.1 over s. And now this is a separable differential equation. In fact, even better, it's not only a separable differential equation, but think about this as you would in Calc 1, dy dx, or in Calc 2 equals 1 minus 0.1 x to the negative 1. Well, all you really have to do is integrate both sides with respect to x, because the right-hand side depends only on x, and so the integral of the derivative of y is just equal to y, and the integral of 1 will just be x minus, and then here we have to use the power rule for integration, so we are going to take the integral of 1 over x. Oh, I'm sorry, the integral of 1 over x is the natural log of x. So the natural log of x. And so in terms of our variables, that is, y is really I, and it depends on s, where x is our s, and we just solved for the number of infected people in terms of the number of susceptible people. So I can always tell you now how many people are infected based on how many people are susceptible. So this is actually going to give me a perfect sketch of our phase plane. Let me go over to Desmos here. Just a couple of, just one minor and important change here. ds dt was negative 2si, so we should have a negative here and a negative here, which makes this a plus and a minus. This will be minus and plus here, and same thing goes here. It should be minus 1 plus 0.1 x to the negative 1 minus x plus minus s plus, and we should also have plus an arbitrary constant here, a plus c, which will be based upon our initial condition. And if we go ahead and graph this in Desmos, not surprisingly, what we see is the exact same curve that we started off with. In this case, I just have an initial condition that says that when there are there's one susceptible, there are 0 infected. So assuming everybody's susceptible at time 0, you can see what happens. The number of susceptibles is dropping, and the number of infecteds is on the rise until it hits this point. And as susceptibles continue to drop, so do the number of infected. And in this case, we end up with a final value of 0 susceptible, 0 infected. So it does make sense that everybody, in this case, all the susceptible became infected, all the infected became removed. And so now, by the time this point happens, which remember, this is not a time graph, but by the time we get to this point, we are effectively, everything is over. The disease is done. And that's pretty much it. This is the phase plane that we observed, and this sometimes is a nice little gift that occurs whenever we try to kind of exploit the structure of differential equations, and in this case, dividing them, we came up with a different rate. We omitted time from the picture, and we were just able to plot the number of infected given the number of susceptible. So that's it. This is the SIR model. I encourage you to play around with it and experiment and make up scenarios and look up scenarios and see if you can also do some research on how to modify this thing. For example, if people can become reinfected.